Good morning. Today I am going to present the research paper titled BERT Pre-training of the Bidirectional Transformers for Language Understanding. I am Kitsiri Chakuri. The main motivation of this paper was to develop and improve the language model with context-sensitive features from a left to right and right to left with sentences. Currently, language models such as OpenAI GPT uses a left-to-right transformer, whereas ALMO uses the concatenation of independently trained left-to-right and right-to-left LSTM to generate features and downstream tasks, as shown in the figure. Before moving to the model architecture, I'm going to give a brief introduction about key concept of the BERT paper. First is embedding. According to this sentence example, I can develop a neural network. Tokens are identified with the language dictionary as shown in the figure. So I is identified as number 1. Then with the support of the vector table, corresponding vector with 8 dimensions is selected as shown in the slide. Each dimension represents a numerical value. When it visualized with the dimension, it is as shown in the figure A. Then in the following figure B represents the visualizations of different words in a vector space. As you can see in the following figure, similar words tend to be near as shown here. Now let's have a look at how language models work at the beginning. Basically, the language translation was done with a sequence-to-sequence model. When an input sentence is given, corresponding hidden vectors are generated iteratively, and the final hidden vector is used as the input to the decoder. But due to this approach, most context get lost. The following figure, the down figure, shows the improvement to this model with the addition of the attention. In this approach, rather than taking the final vector, all the generated hidden vectors were used to generate the final language model. Then, the next enhancement of the language model is the introduction of transformers. This was introduced with the attention all you need paper. For the first time, missing the context problem was eliminated with the attention technique. Rather than using the recurrent approach as I explained you earlier, embedding of each word was generated by looking at the context of every other word from left to right as well as from right to left. As shown in diagram A, transformers consist of main two components, encoders and decoders, as shown in figure 2. Encoders consist of attentions as well as deep neural network, and the deep decoder consists of encoder and two attention. In real implementation of the transformers, it consists of 6 encoders and 6 decoders, as shown in the figure C. From there onwards, we can move into the BERT model. Comparing to the transformers, BERT has few changes. First, it consists only encoders, elimination of the decoders. Then there are 12 encoders instead of 6. Figure B illustrates one transformation layer as shown here. Usually it takes embedding as input and process with attention layer and with deep neural network layer before giving the final embedding output to the next BERT transformation layer. This slide shows few differences how the word represent in BERT architecture. Start of the word represents with CLS tag, and the sentence separation is represented with SEP tag. Initially, as shown in the previous slide, this model was trained with two tasks. The first is Musk language model, and the other one is the next sentence prediction. For the training, some of the words were masked to predict at the end, and the entire training was unsupervised. Regarding the embedding of the model, final embedding was generated after concatenation of vocabulary embedding, segment embedding, and the position embedding. Segment embedding is used to identify two sentences separately in next sentence prediction task. Position embedding is used to represent the position of each word in a given sentence. Sign function was used by that time for the identification of the position. Then the final embedding was flowed through 12 layers as shown in the diagram. Corresponding output of the first token concatenate the context of the other embeddings and generate the output for the next sentence prediction. And there are three prediction output to generate the mask words of the given sentence as shown in the diagram. And the cross mark represent the ignorance of other words as output. Then the slides talk about the attention. This example with the sentence. Deep learning is used to illustrate the embedding generation step for the word deep. Initially, the embedding vector is multiplied with the query, key, and value matrix to generate the query, key, and value vector. Then the query vector is multiplied with every word's key vector and with its own key vector. Then softmax function was used after the division operation as shown in the figure to generate a number to be multiplied with the value vector of each word to generate the corresponding context embedding from each word for the deep word. I would repeat it for the deep word. Finally, those context embeddings were added together to represent the final context embedding vector for the word deep. Similarly, it was done by that time for all the words with the attention in BERT model. In real implementation, it's only matrix-matrix multiplication instead of vector matrix multiplication. As shown in this slide, BERT has multi-headed attention. Actually, it's 12. Previously, I discussed about one attention. Likewise, 12 different attentions run parallelly for each word, and the output from each attendant hit is linked together to generate the final embedding of the word before it linked with the deep neural network. Exact dimension of the embedding layer is 768, and each attention generates an embedding with 64 dimension as told earlier. The multi-headed attention run for each word and generate the embedding. Each word then entered to a deep neural network and execute parallelly until it gives the input to the next BERT transformation layer. As explained previously, BERT was trained with tasks with pre-training, and 11 different NLP tasks were used with fine-tuning. Book corpuses and English Wikipedia was used for those tasks. Compared to pre-training, fine-tuning is relatively inexpensive. BERT base contains 110 million parameters and BERT large contains 340 million parameters. So most of the time, BERT large has given good performance compared to BERT base. This slide shows the performance improvement of several tasks with BERT fine-tuning, such as question answering, dataset, and then adversarial generation datasets. As the paper discussed, significant output was generated with each evaluated tasks. Regarding the advantages and disadvantages, the advantages are quicker development, less data requirements, achieve state-of-the-art performance on large suites of sentence level and token level tasks, and it effectively addresses the ambiguity. As disadvantages, slow fine-tuning, slow inference, and less performance when there are technical jargon words when they try to execute some tasks. So, regarding this paper, I would like to summarize it with the following key points. Results enable even low resume tasks to benefit from deep and directional architectures. BERT deep bidirectional architecture allows the same pre-trained models to successfully tackle broad set of NLP tasks. Thank you.